Good morning to everyone. Myself, B. Krishna, Assistant Professor, Department of ECE, Adhikavan City. Today's class in bipolar junction transistor, I'm going to discuss about BJT configurations, bipolar junction transistor configurations. In that, I want to discuss in detail about the input, output characteristics, and also the forward bias, reverse bias conditions of the bipolar junction transistors. So how it is going to perform the input characteristics and output characteristics, all those things are going to discuss in this class. So BJT bipolar junction transistor configurations. Okay, we have seen that here the first point here we have seen that base is taken as common point or terminal to connect a transistor in common base configuration. Similarly, emitter and collector is taken as common point or terminal to connect the transistors respectively. Call it as common emitter configuration and common collector configuration. Okay. Thus, the transistor can be connected in a circuit in the following configurations, such as first one is common base configuration, and second one is common emitter configuration, and third one is common collector configuration. Let us see the circuit diagram and input output characteristics of these configurations in detail. So this is the basic circuit diagram of common base configuration of bipolar junction transistor. Okay, and here the base terminal is common to both input side as well as output side. That's why here we want to say it is a common base configuration. And this is the structure of bipolar junction transistor in common base configuration. And here we can apply the input voltage between emitter and base. Okay. Similarly, the output is between collector and the base. Right? Let us see here. Here, this is a NPN transistor. This is the N, and this is the P-type layer here. Again, it is N-type. Okay. So here N-type region means the emitter is a N-type region. It is having majority charge carriers or electrons, means it is negatively charged particle, negative charge area. For that, again, we are injecting the negative potential here. And here base is a P-type layer here. It is having positive charge and is more. Okay. For that, again, we can apply the, we can injecting the or connecting the positive potential here. So then the emitter base junction is called as forward bias condition. Similarly, the collector base junction here, that is VCB here, it is the N-type region collector. Negatively charged ions are more here. For that, we are giving it is a positive potential. For positive charge region, we are giving it is a negative potential here. Then the collector base junction is going into reverse bias condition. Okay, this is the internal structure of NPN. It is having one junction, that is emitter junction. This is the collector junction. Okay, so by applying this potential here, biasing voltage here, the electrons are entering into this, and then the current will be going in the opposite direction. Okay, so by this applying potential voltage here, then some of the charge carriers are recombination is occur across recombination going in this particular base region. then we are expecting there is a current. That current is nothing but base current here. So here the positive charge ions are more. We are applying again positive terminal. Then the charge carriers of holes are moving towards the N region. That the same way is also having the current here. That is nothing but base current. Okay. And remaining few of our recombinations occurred in this base region. The remaining 98% of charge carriers are entering into the collector region. Then they are moving in this direction. Then the current is going to like opposite direction. It's nothing but collector current. This concept is already we learned in last classes, right? Now I want to go with input characteristics here. Okay, so let us see. It is the graph representation for the input characteristics of common base configuration. Okay, let us see here. So this graph is shows the relationship between input and input current, that is IE here, and the input voltage VBE for different values of VCB, collector base junction biasing voltage. Okay, right? It is shows the input side here, input current and input voltage, relation between the input current and input voltage for different values of VCB. Okay, so it represents as a like here this region nothing but is actually a forward biased diode. Okay, so here let us see here as IE is increases, IE is going to increase as we are going to increase the VB. Initially VB is going to like this. So here it is a silicon transistor. The cutting voltage for silicon transistor is 0.7 like that. Okay. As IE increases, as VB increases for a fixed values of VCB. Let us see here. This is the IE value, IE current, emitter current in milliamps. It is going to in increasing order as we are increasing the base to emitter voltage for different values of this collector to base voltages. Okay. So then here, let us see here one more point here. As VCB increases, the width of the depletion layer is increases in the base region. Okay. So let us see here as VCB is going as VB is going to increases, as VB is going to increases here, then it is going to forward bias condition automatic, as well as the current emitter current is also going to increases. Whereas VCB is going to increases, VCB is going to increasing order. Why? Because it is a reverse bias condition. Then the junction JC is going to act as a reverse bias. By increasing this value, by increasing this value, then the depletion region is very wider, and then it will be affecting the base region. Affects the base region. How it is affects in the base region mean the width of the depletion layer in the base is increases. Okay, so means here the width of the this depletion layer will increases in the base region. So hence the width of the base available for conduction is decreases, right? Hence here the width of the base available for conduction is decreases because of due to the different values of we collected base voltage going to increase. Then the depletion region at JC is going to wider. It will be increases. It occupies the some of the space in the base region. So means the conduction of base region will be decreases. Okay. So thus reduction in the width of base due to increase in reverse bias voltage, that is VCB, that is VCB here. Okay, in reverse bias condition is known as early effect. Okay, again I repeat you, the reduction in the width of base, the reduction in the width of base due to increase the reverse bias voltage, increase the reverse bias voltage is known as early effect. Early effect, right? Okay. And here, one more thing is here, due to this recombination of electrons with holes in the holes in the base is also decreases. Okay. Further, it is the VCB collected to base voltage further going to increases. Further, it is going to increases here. Okay. At one stage, at one stage, completely, completely, the depletion region at collector junction is completely occupies the base. So this phenomenon is called as punch throw effect. Punch throw. Okay. Again, I repeat you, as VCB further increases at one stage, the depletion region completely occupies the base at which the collector base junction breaks down. This phenomenon is known as punch throw. Okay. This is a basic concept of input characteristics here. Okay. So here, this concept is also available in a practical laboratory also there. You have to do this. Okay, bipolar junction transistor input and output characteristics for different configurations such as a common emitter configuration, common base configuration, common collector configuration. Okay, for this case here, VB is going to increases, VB is going to increases. Okay, then collector emitter current is also going to increases where different values of VCB. Okay, coming to the output characteristics here, so it shows the here it shows the collector current and collector to base voltage. It shows the relationship between the it shows the relationship between the collector current and the collector to base voltage here, right? So here let us see, we can observe the three regions here, such as one is cutoff region, other one is active region, and third one is saturation region. The same regions also here, let us see here, it is active region, and this is the cutoff region, and this is the saturation region, right? Here, so this graph is define the relation between IC and VCB at different values of IE, right? So coming to these three regions, out of first one is it is cutoff region where both junctions are in reverse bias condition. As I told you in previous classes, for bipolar junction transistor basic operation, there the device is going to operating in three modes. It is necessarily going to operate in three modes, such as one is cutoff mode, active mode, and saturation mode. Whereas in cutoff region nothing but it is a cutoff mode, then both the junction, emitter junction and a collector junction, both junctions are going to reverse bias condition. Okay, so here if let us see here, if it is reverse bias condition, okay, if it is reverse bias condition for n region we are going to positive, and here for P region, here we are going to negative, then what happened here? There is no movement of electrons in the emitter region. So means we get there is a zero current. That current is due to the emitter terminal. Nothing but IE is zero. IE is zero. So like this. Okay. So here when the emitter base junction is reverse bias, the current due to majority carrier is, that is IE is zero. Okay, when the collector base junction is reverse biased, the current due to minority carriers flows from the collector to the base is represented as ICBO. ICBO. That is also a very small amount of current. It is also negligible. Nothing. It is zero, right? Zero here. So means in cutoff region both junctions are act as reverse bias condition. Due to that reverse bias condition, at the input side there is no movement of charge carriers, and in the emitter region that constitutes a current. That current is emitter current. That is zero. That is zero here, right? That is zero. Let us see here. This is the IE equal to 0 milliamperes. Similarly, the collector base junction is reverse bias condition. It by applying the reverse bias condition, the junction at collector is wider. There is no movement of charge carriers. Why? Because the junction collector junction is the reverse bias condition. There is a small amount of carrier will be moving from collector junction to base junction. That carriers are nothing but reverse charge, minority carriers. Due to that minority carrier, there must be a current. That current nothing but reverse saturation current, but it is practically negligible. So means IC is also zero, IE is also zero, nothing but the device is in cutoff mode, right? Whereas in active mode condition, the emitter based junction is forward bias condition and the collector based junction is reverse bias condition. Okay. So once VCB reaches a value larger, once the VCB will be reaches a larger value to ensure a large portion of electrons enter in the collector, IC remain constant as shown by the horizontal line. Okay, here this is the IE here 2.5 milliamperes like that. Suppose want to go like this here. First one here to identify this one is point here. Here VC is initially it is zero. Initially it is zero here. Okay, for the larger value of or large value of VCB, VCB nothing but it is a VCB nothing but it is a voltage at collector to base region. So means similarly the active mode the emitter base junction is forward bias condition. Due to that forward bias condition, the maximum amount of charge carriers are enter into the base. But out of this maximum, very few of our recombination is occur. Remaining are entering into the collector region. Collector region. So then the VCBs also have larger value. Then that will be maintaining the collector current is constant like this. It is maintaining the constant value along the x-axis. Because IE equal to, as I told you in previous class, that is in current components, IE equal to, sorry, IC equal to alpha into IE here. Okay. So here IE means emitter current, alpha is nothing but 98% of charge carriers. 98% of charge carriers are entered into the collector region. So that is equal to nearly 0.98. This is equal to 1. So then alpha equal to 1, then IE equal to IC. So means it is maintaining the constant value. IC equal to IE. That is constant level along the x-axis in a horizontal line. As IC is increases, then automatically IE is sorry. As IE is increases, IE is going to increases as well as IC is also increases. Okay. As IE is going to increases, then as at the same time IC is also going to increases. Why? Because they are almost equal, almost approximately equal to each other. The collector current and the emitter currents are approximately equal to each other. Then as IE is increases, then collector current is also going to increases. Right? That is nothing but active region. So coming to the saturation mode, here both junctions are forward bias condition. Right? Both the junctions are nothing but emitter base junction JE and collector base junction JC are both are in forward bias condition. As here VCB, how the collector base junction is going to reverse bias forward bias condition by decreasing. So the VCB value is going to in it is negative direction. Negative direction, right? The collector base junction is now actually forward bias. The graph are drawn on the negative side here, okay? So here the emitter base junction is forward bias condition, the collector base junction is forward bias condition. Now the graph is like in the negative side here, nothing but it is a saturation current. So this is the output characteristics of common base configuration, right? Next, current amplification factor here. So it is the ratio of change in collector current to the change in emitter current at constant collector based voltage, that is VCB. That is alpha in alpha AC equal to delta IC by delta IE at VCB is constant. Change in collector current by, it is the ratio of change in collector current by change in emitter current at VCB's collector to base voltage is constant. But it is generally it is considered in a DC value. DC value alpha DC equal to ratio of collector current by emitter current. Right? This is the concept of common base configuration. Coming to the common emitter configuration. So similarly, common base configuration. So here the common terminal emitter E terminal is common to both input side and output side. Okay, this is the emitter terminal. It is the input side here. Okay, and this is the output side here. So emitter terminal is for common for both input side and output side. Okay. Here, the input is applied in between base to emitter VBE, and output is taken between the collector and emitter, that is VCE. This is the structural representation of common emitter configuration, right? And here, I want to go discuss about the common emitter configuration in detail of input and output characteristics of common common emitter configuration. Okay. Let us see the characteristics here. So let us observe here point here. The base, the VC is the base current is shifted some points left on the x-axis. How it is happen? Let us see here. So it shows the relationship between the input current IB in microamperes and the input voltage VBE, that is base to emitter to base junction, for different values of VCE collector to emitter junction. Okay, so here the input current IB is increases as input voltage VBE increases for a fixed value of VCE. Okay, so here as VCE increases, as VCE is going to increases, so here VC is going to 1 volt, 20 volts and sorry 10 volts and 20 volts. As VC is increasing, thus the depletion in collector base increases. The depletion in collector base is increases, which decreases the width of the base available for conduction in the base region. Hence, IB is going to decreases due to early effect and the graph shifted towards the x-axis. Okay, as VC is going to increasing order, then the collector base junction is increases, that will be decreases the width of the base region. So means the base current will be decreases, that will be shifted or that will be shift towards the x-axis due to the early effect. Due to the early effect. Hence, here the IB is decreases due to that early effect. It was shifted the along the x-axis. And here for VB is going to increases, VB is going to increases and IB is also will be increases at these values. So this is the current input characteristics for common emitter configuration, right? Coming to the common emitter output characteristics here, similarly it is showing the relationship between the collector current and collector to emitter base junction, collector to emitter voltage. And here let us again, here we are observing three regions here: cutoff region and active region and saturation region. Okay, here also again we are observing the three regions here: cutoff region and saturation region and active region. Okay, coming to the, so here let us see the, let us observe the three regions, such as one is cutoff region, active region and saturation region. So in cutoff region, as I told you in the previous slide, The cutoff region, both junctions are in reverse bias condition. So this is junction 1 here, okay, and this is the junction 2 here, okay. So here both junctions are going into reverse bias condition, reverse bias condition, okay. And here active mode, coming to the active mode device, here emitter base junction is going to forward bias condition, and collector base collector junction active mode emitter base junction is going to forward bias condition, and collector base junction is going to reverse bias condition. As I told you in the previous class, here in active mode device, always the emitter base junction is going to forward bias condition, and the collector base junction is going to reverse bias condition, okay. So coming to this saturation mode, both the junctions, emitter base junction and collector base junctions, are going to forward bias condition, right? Next, the current amplification factor here, it is defined as the defined is the change in collector current to the change in base current as constant collector emitter voltage VC. That is beta equal to change in delta IC by delta IB, nothing but change in collector current by change in base current at constant value of collector to emitter voltage, that is VCE, but it is generally considered in a DC value, that is beta equal to IC by IB, right? Again, I told you here, cutoff mode, both junctions are reverse bias. When the emitter base junction is reverse bias and current due to majority carriers is 0, right? And here, when the collector base junction is reverse bias, the current due to the minority carriers flows from the collector emitter junction is represented as leakage current. It is leakage current. Coming to the active mode, the emitter base junction is forward bias and the collector base junction is reverse bias. As IB is maintained constant, current IC increases at reverse bias voltage VC is increases. Okay. As I told you in previous slide, that is a common base configuration. Here, the base current maintaining a constant, that constant current IC increases at reverse bias voltage VC is going to increases, okay. See here, VC is going to increases and maintaining the base current is constant here, and the collector current will be going to increase in order, right? It is in active mode. So coming to saturation mode, both junctions are in forward bias, that is junction J1, junction J2 are both are in forward bias condition, okay. In this region, there is a large change in collector current with a small change in VCE, okay. So here let us see here, so zero VCE is 0 here, very small changes occur across this point. Let us see here, the collector current is very huge current is occurs, means very small amount of this VCE from 0 onwards, the collector current is this like this, okay. This is the output characteristics for the common emitter configuration. Next, common collector configuration here. Common collector configuration. Here, I want to take a collector terminal as is common to both input and output. So here, the collector terminal here at the input side and output side is taken as common terminal here. Here, we can make it as a ground terminal here. Now, the input is applied between base and a collector, that is VBC, and the output is taken between emitter and collector, that is VEC. So this is the structural representation of common collector configuration. So coming to the input characteristics here it shows the relationship between input current IB and the input voltage VBC for different values of VC here. So here the common collector input characteristics are quite different from the common base or common emitter input characteristics. How it is different? Because of here the difference is due to the input voltage VBC largely determined by the level of output voltage VCE. So here VC equal to VCB minus VB. So here VC nothing but this one, this much of voltage here. VC equal to uh, here VCB plus here VB. Okay. So here the VCB equal to VCB nothing but here VC equal to VCB minus VB. Suppose here the VCB is going to large drastic here. Let us observe here. This is a VC equal to VCB. Suppose here VCB is 1.7 volts and VB equal to it is maintaining a 1 volt, like the VC is 1 volt here, 1 volt here, and VCB is here is 1.7 volts here, VB is 0.7 volts here. So then let us observe here that value is 0.7. Difference value is the 0.7 here. So means for drastic change, 0.7 means the base is going to be the base current will be going to decreases. Okay. Once observe here, VC equal to VCB minus VB. VC equal to VCB minus VB. Okay. So here VCB equal to VCE plus VB. So here VCB nothing but uh, here by drastic changes in VCB, that base current will be going to decreases. So by increasing this voltage here, the emitter base junction is going to voltage will be going to decreases. That is in terms of 0.4 volts. But for silicon voltage, it is 0. VB is 0.7 volts. So if your applied voltage exceeding this level, then the base current will be going to entering. So the device is going to in the emitter base junction is going to forward bias condition. Then only the emitter base junction is going to forward bias condition. But here VBC is the base collector voltage. When the base collector voltage will be going to increasing order, loss drastically changing, then automatically the base emitter junction voltage will be going to decreases. If it is decreases, then the base current will be suddenly decreases. Okay. So here when VBC is increased by keeping VCE constant, VB is decreases, which decreases the IB. Okay. Here VBC is increased by keeping VCE constant. So here by increasing VCB, keeping VCE constant, at the same time VBE emitter base voltage is going to decreases. If the emitter base voltage is going to decreases, then base current is also going to decreases, right? So coming to the output characteristics here, so here it is the relationship between VCE and IE at different values of IB. So it is here, let us show here, it is the relationship between the output current IE and output voltage VCE for different values of input current IB. Since IC is approximately equal to IE, how it is happened? By the whereas going to the common emitter configuration, so here the IE is maximum amount of electrons are entering into the collector region. So then IE is approximately equal to IC. So the common collector characteristics are identical to the common emitter output characteristics. Okay, and here let us again see the current amplification factor here. It is defined as the ratio of change in emitter current to the change in base current with the respect to VC as constant. But it is practical, it is generally considered as the DC value, that is gamma equal to IE by IB. Right? Thank you.